Hello. In this video, we're going to look at 4 distinct ways that you can model or represent a spring mass damper system in Simulink. Our very first step is not actually in Simulink, it's in MATLAB, and it involves creating workspace variables that our Simulink model is going to reference. So to do that, I'm going to open up this MATLAB script called bhscript1.main. So let me just open that for you now. So here's the script. Let me run it from top to bottom by clicking this green run triangle. And you'll see that by executing the script, we've now created 6 or 7 MATLAB variables in the base workspace. M, for example, represents the mass, K represents the stiffness, and a variable such as x0 represents the initial position of the mass. Yeah? So step 1 is we've now got parameters defined in the base MATLAB workspace. Step 2 is we're going to open the Simulink model called bh1.hello. So let me open that for you now. And here it is. And it shows the 4 different modeling approaches for representing a spring mass damper. There's method A, method B, method C, and method D. And for each of the 4 different modeling methods, we're going to take the position signal and we're going to plot it on that big pink scope. So let me open up the scope for you right now. So each of these 4 axes corresponds to the green position, method A, the yellow position, method B, and so forth. Let me run the sim. And there it goes. And if you eyeball the top 2 traces and the bottom trace, they kind of look the same. And you'll notice that the second from the bottom trace, the purple trace, it's the odd one out. Clearly it's missing out on that first phase of transient behavior. And you know what? That's actually not a surprise, because this method C output that we're looking at corresponds to the transfer function approach for modeling. And the transfer function approach assumes that all internal initial states are 0. Yeah? However, methods A, B, and D all are able to sort of adequately represent non-zero initial states. Yeah? So the conclusion is that methods A, B, and D all produce identical results, which is quite reassuring. So let's have a bit of a look at 2 particular methods. So method A sort of shows how when you start out with the provided mathematical description for the system dynamics, in this case the classic second order ODE, you then use the core Simulink blocks, things like integrators, gains, constants, and so forth, to represent the provided ordinary differential equation. So that's method A. Method B is very, very similar to method A. You can sort of see that it still contains the classic integrator pattern. That is that if you have this thing called x double dot and you integrate it, you'll get x dot. And if you integrate x dot, you'll get x. The big difference between method A and method B is that we're going to use a MATLAB function to define the expression for acceleration. In method A, we represented that acceleration by using, these core Simulink blocks. But in method B, let's have a look what's inside this MATLAB function block. Yeah? Remember, before we do, this MATLAB function block is supposed to be outputting an acceleration signal. So let's just have a look at how it computes that acceleration signal. So when I double click on that MATLAB function block, it reveals the MATLAB code that is sitting behind it. And you can kind of see that all of the system inputs for that block all appear as standard MATLAB input arguments. and the system output from the block, you'll recall that was the acceleration signal, that corresponds to the output argument in the function. And sure enough, you'll see that the acceleration output is simply the same classic formula for the spring mass damper dynamics. So there you have it. We've got 4 distinct ways of representing a spring mass damper, and we've spoken to 3 of them: method A, B, and C. Thanks for watching.